Hi everyone, I'm Bowen. I'm going to give you guys today a talk about large-scale decentralized pre-training. And basically this is going to be a little bit of more of a theoretical talk compared to the other talks, but I hope you'll enjoy it as well. So let's just first ask ourselves, like, why do we want to decentralize pre-training, right? Why focus on pre-training? Because there's also post-training, there's fine-tuning, there's RL, all those other training cases. So basically, we'll talk about like three major reasons why we want to decentralize pre-training. So the first factor is economic. Most of the costs incurred during training is in the pre-training, right? So if you compare the cost of fine-tuning or post-training with pre-training requires massive scaling, much more compute and much more data. So post-training has a much smaller scaling requirement compared to pre-training. So this is why decentralized pre-training can help, right? And decentralization helps scalability, helps cost, and efficient use of global compute. So here you can see this is a chart from one of the, this is a chart from one of the institutes of AI research, and they showed that the data center cost, basically the power cost and everything is just rising exponentially every year. So if we give some more context, so there's first compute utilization, right? So this advantage gives us the better use of idle compute and off-demand compute. So as you possibly know, possibly in your clusters, there could be like idle GPUs right now. Like us at Nous, we know that the compute is not always fully utilized. We buy like, if you bought a server, it's probably idle like 25 or 50% of the time. Secondly, there's energy efficiency, which means here you have renewable energy, right? There's also off-demand, off-peak energy. So, for example, at noon, people are mostly not at home, they're using less energy, but when you go back home, everyone uses more energy. So if the training can happen during those off-peak hours, you can better utilize energy across the world. And thirdly, and finally, for this one is pooled resources. So if you train a whole pre-trained model, you have to do it by yourself, right? If it's centralized, so you have to pay everything. So the data center, the cost, the data. But if you can kind of pool resources with other companies together, so now you can maybe train 10% of the model and own 10% of the model, right? So that's kind of amortizes the cost over time. So you can possibly go into it not like immediately by just training a 400B. You can start participating in a bigger run, but you only pay 10%, and then you can scale up. So this gives also incentive mechanisms to this. So the result is a much lower barrier to entry for pre-training. So as far as I know, people that pre-train are like very, there's not many companies that do pre-training. So this possibly could change this problem. So secondly, the second reason is data and privacy. So this one is very interesting because this allows us to leverage diverse local and private data sources. So pre-training is the best way to take advantage of unsupervised and large-scale self-supervised data sets. So this is why you want diversity and variety. So how do you do this? So this reason, not how do you do this, but the privacy and data part, the first part is the local and supervised specialized data, sorry. This allows independent contributions to training. So if you have everyone that's training decentralized, you can contribute your own data to it. So that is one of the possibilities. There's also privacy. So there are a lot of high quality private data sets. For example, people that do animation, right? People that do 3D work. There's also a lot of artists. There's also medical data that you don't want to be public. And also sensitive data, so possibly like other cases where state secrets or something, but I'm not very sure about that. But this second part is also known as federated learning. I'm pretty sure you guys have heard about this. And the result of having this decentralized training is that you have higher data diversity, which potentially increases the model capabilities, right? And the third one and last one, but not least, is trust and resilience. So this, by doing decentralized training, you reduce dependence to centralized authorities. So increase reliability and transparency. So let's start with transparency. This allows us to create reproducible models. So how do you train a, for example, Llama 2 model? We don't really know. There is the paper, but it is not reproducible. So it's not really like perfect open research, right? Currently, SOTA model recipes are all hidden from the public. So for example, DeepSeek model, Kimi model, all of those very big models, very good models, you can't really replicate them one-to-one. So if you really tried to go through the paper, there's like still stuff missing, there's no code, and etc. So yeah, and this is also very important for collaborative and open research. Because by doing pre-training, this allows you to test out new architectures that you cannot do in fine-tuning or post-tuning alone, right? So if you have, let's say you think about new architecture, how do you like create a new LLM, new transformer? You really can't if you only depend on those big labs. And the last one, I'm sorry, yeah. And the last one is safer AI research, because now you don't have security by obscurity. So right now, people, what they do is they kind of align the model, right? They call it model alignment. But that is basically security by obscurity, because you're not really telling people, like, how do you do this, right? The model just refuses requests, but if somehow the model leaks, or someone steals the models, they can remove this, and you don't have security anymore. The second part now is resilience. If you have very decentralized networks training models, you don't have a single failure point. So you don't have like a singular attack point or failure point. And there's also true model ownership. So the people that train the model would own the full model. So if you didn't do the pre-training and you only took a already pre-trained model and you fine-tune it, it's not really yours. You could call it your model, but it's not technically yours because you're dependent on them. And this one, so the results is it accelerates OpenAI research and improves safety by a lot. So yeah, hopefully I've convinced you why we need decentralized training. So let's talk about the open challenges now. The first one, so I call this the 4 pillars of decentralized training because they're kind of the 4 pillars that are needed to achieve it. So they're not completely independent, but you can, let's start with the first pillar. So this one is optimization. So how do you keep convergence equal to centralized training given the major constraints by the internet's architecture? So here you can see this is a typical like client to server connection where you have many, the path of from this computer to the server, you have many different nodes in between, so it adds latency every time you go through. And some of the nodes are much wider in bandwidth, some of them are narrower. So if, for this case, if we assume, let's just assume perfect reliability and homogeneity, we still have 2 major problems. So the first one is a limited bandwidth, right? So on the internet, you have, on average, in data centers, 128 or 125 megabytes per second. That is like the average link. There's some that are higher, for example, 800 megabytes per second. We're talking about bytes, not bits here. So usually internet speed is measured in bits per second, but if you divide by 8, it's bytes. And on the NVIDIA HGXs, you can see it's 1.6 terabytes per second. So there's 4 orders of magnitude of difference. So that is very, very large. And the second one is the high latency between accelerators, where you can see on the InfiniBand or NVLink, it's less than 100 nanoseconds. So it's very, very quick. But on the internet, it's more than 30 milliseconds. So if you have a link between, let's say, Detroit and New York, that's 30 milliseconds at least. So that's 6 orders of magnitude of difference. So let's just focus a little bit about on the bandwidth, right? So if you focus on the bandwidth, you have potentially one solution, which is gradient compression. It's used with distributed data parallel or also FSDP, fully sharded data parallel. The only problem with gradient compression is very difficult to scale up. That is because if you think about a 1 trillion parameter model trained over the internet, compressed to 99%, it's still 10 gigabytes, right? And 10 gigabytes is still, it will take you a lot of time. And if you have many, many nodes that have to communicate 10 gigabytes, it overwhelms very quickly. So the only solution is basically improve the convergence of gradient compression. So improve the compression algorithm itself. But as always, too much compression leads to worse convergence at scale. So then you also have activation compression, which is also another way of doing it when you go through the forward pass and backward pass. So this is used with tensor parallel and pipeline parallel. So you can split the model in multiple parts and give every accelerator a different part of the model and communicate that way, right? But this is very robust to low bandwidth because you can kind of do multiple passes at once. But it's very sensitive to latency because you have to do one step at a time. And it's very slow over the internet. So there's something called a zero bubble when people try to do pipeline parallel, where they try to minimize the wait time, like minimize the empty space of the pipeline. And that's very hard to do in practice over the internet because you have so much variability in the latency. So some nodes are slower than others. Sometimes one becomes slower over time or becomes faster. So it's very, very hard to manage this. And also, just both of these methods, too much compression harms convergence. So if you don't have the full gradients, you have an approximation. When you train at big scale, it just doesn't work anymore. And the second constraint is high latency between accelerators, right? So between all of those nodes, maybe one is in China and one is in the US. How do you coordinate everything? One of the solutions is potentially asynchronous training. So you train independent models on different islands, right? So if you have multiple accelerators close by, you train them together, and then you sync occasionally between those very far away nodes or accelerators. That is very good, like theoretically, but in practice, it's very messy, and it's hard to derive the convergence, especially because of gradient staleness. So gradient staleness is when the gradient is less informative. So if you train one node, one part of the country, like one model, and the other part, another model that don't sync together, over time they kind of diverge, right? They're not the same model anymore. So it's very hard to merge them back together. So if this can also be taken to the extreme, there's recent papers that show that you can train, let's say, 5 models completely independently and then merge them back together at the end. But this is kind of similar to model merging or model ensembles, right? So that becomes another question. It's not even training anymore. So yeah, too many islands harm convergence at scale. So here there's like a diagram from the paper De Loco where they show that you can train inner steps and then merge multiple models and then retrain the inner steps. Yeah, so that was the first pillar, which was optimization. That one is basically the most basic thing that we need, right? And we're not quite there yet. So decentralized training is still kind of a dream because there's no like real optimization algorithm that solves everything. For example, for my paper demo, the couple momentum paper, that one is gradient compression, but also has like a lot of problems with scaling. Yeah, but let's go to the second pillar, coordination. So here, we are dropping the previous assumption. So remember, we were talking about perfect reliability and perfect like homogeneity. Now it's completely the opposite, right? Now we have in the real world, you have heterogeneous hardware. So you don't, like every node is different. Some nodes are faster than others. Some have more power. Maybe some are newer than others. So you want to like kind of reuse older hardware. So different data centers and individual machines might have different hardware. And that means variable GPU speeds, network speeds, etc. There's also unreliable hardware. So some machines on the internet may not be reliable, and even the internet itself is not always reliable. So there's packet loss, routing problems, and etc. Yeah. So this one is also highly coupled with the previous one because we'll talk about this in the next slide. So let's focus on the heterogeneity problem, right? The first of the solutions is load balancing. This one is the most obvious one. So what you do is try to give more work to some accelerators than others. So for example, we can try to do predictive scheduling. And the question is, how do you detect the accelerator speed in advance? So how do you know that this data center is faster than the other? So you have to give work in advance, right? So what would happen if one of them just slows down unexpectedly? It's very hard. So if you don't handle this properly, the training will be slowed by the slowest accelerator. So it will be dragged down, right? So you need to adapt the optimization process, which makes the update size non-uniform. So in some sense, when you train, you want to assume IID, so identically and independently distributed data. But if you train some nodes more than others, now you have this like non-IID problem, a non-uniform update size. So this is a very open question, open challenge, if anyone is up to the task. The secondly is coordination. Again, coordination is reliability, right? So if you want to make the training reliable, you have to have fault-tolerant aggregation. So it means that the accelerators can return faulty or no data. So sometimes one node would just not train for some reason, right? It doesn't do anything. And now we want to constrain this to assuming no malicious intent. So hidden gradients, when we're talking about the past gradient compression and asynchronous training, you have hidden gradients. So in asynchronous training, you don't see the full gradient, right? They're training like 500 steps alone, and then you see the update. So how do you detect the fault if they're doing it alone, right? It's almost impossible. So this is a very, very hard problem that you need to adapt the optimization algorithm same as before. And it's also very open, this challenge. Yeah, let's then go to pillar 3. It's also, there's 4 pillars. So this is a pretty complex task, but I'll try my best to give an overview. So now we're assuming public training data and training updates are like public, right? So if the training data and the training updates are public, there are problems to decentralization. The first one is free riding. That means some people can send valid but like old updates, right? They kind of trick you to think that they've done the work, but they haven't. So they copy others' work. So maybe someone was doing the work and then just copy its work and submit it before them. So you would get credit without doing work, and that's not very good. It also slows down the training because it undermines incentive mechanisms. So if you reward people for doing work so that they do the work, they do this, you won't really have a good training run. There's also model poisoning, which is when people try to inject undetectable like variations in the gradients or add backdoors to your model, right? So they do it over a long time scale. So they take maybe 5 nodes out of the 1,000 and they change just a tiny bit. And if you don't detect that, they can add potentially backdoors. And this can also corrupt downstream applications. So if someone is malicious, wants to target your training run, they can do this. And there's the last one, which is 51% of Sybil attacks. That means that you just basically overwhelm the network with random fake nodes and they all reach consensus, right? Because you have 51% of the nodes saying, yes, this is good, and then your training run just fails. And the last pillar is privacy, which is the federated learning part. So if we drop every single previous assumption, now you have non-IID data. So by this, I mean when you have individual islands training on their own data, right? So the data is not IID anymore. And if the local is local and private, how do we do that? How do you train an efficient model? Some tasks might get undertrained. You might have slow and unstable convergence. And standard optimization just assume IID data. So we don't have any optimization scheme that allows you to do this efficiently. There's also data leakage, where it might be able to recover the original data by looking at the model updates, or even looking at the model itself, right? So in Llama, for example, Llama model, you can kind of re-output some of the pre-training data. For example, some books you can just output the paragraph from the book directly during inference. And the biggest problem is really, how do you verify the work if you don't even know what the work is? So that is the core problem of federated learning, is that how do you verify if someone has done the work without even knowing what they're doing? Yeah, so in conclusion, I know this is very hard, but it's a worthwhile endeavor. And it unifies all the AI, ML, federated learning, blockchain, like cloud computing, unifies the whole stack, right? And the whole communities together. And I hope one of you will be the next one to tackle some of these challenges. Thank you for listening.
Hello.
Yeah, hi.
Thanks. You had a couple of different goals that you could be aiming for. I think like one of the things you mentioned was around verification.
Yes.
Where like if you don't verify the data, that they can put it in backdoors. And then you had the federated learning privacy thing. Is this something that you just have to choose and you can't get both? Like you either have like people can have private data that they contribute, but then you get zero verification, or the other way around?
I mean, it's an open problem, right? So it's not necessarily that you cannot verify, but with traditional verification, you cannot verify the work if you don't know their work. But with cryptographic verification, there's possible ways of doing it. But right now, it's very slow. Like, for example, there's something called ZK proofs, but those are very, very slow. And if you add them to your training run, it would just slow down the training. So it's not efficient, right? So it's really an open question, but it is possible.
I was just about to ask something related to that. So what are you using for differential privacy to prevent leakage and to allow verification of work without stealing? Are you using zero knowledge proofs or anything similar to that? And how do you deal with the bottlenecks? That's just sort of the two things that were popping in my mind during your talk.
Yeah, so do you mean like at Nous, the runs we're doing?
Yeah, yeah.
So we're not doing any of the last two pillars, so pillar 2, 3, and 4, because those are kind of, the prerequisites to them are 1 and 2, right? And even those are not mature yet. So right now we're just focusing on trying to make the training actually work and making the infrastructure stable enough for the training. Because when the internet is so unstable that when we train, there's like nodes dropping, nodes coming back up, and even like nodes coming back up can destabilize your run, because now when you have more compute, right, and what do you do with that? Do you give it a smaller amount of work to everyone? Like that kind of dynamic can also destabilize the run. So it's very an open question right now.
Thanks, that clarified things.
I don't think anyone right now is doing ZK proofs on training yet, but that could be the case someday, yeah.
Can you share how pillar 1 and 2 are highly coupled? You said they are coupled, but...
Yeah. So I can expand a little bit on the 1 and 2, right? Those two. Yeah. As I said to the other question, is that when you have nodes dropping out and coming back online, right? Your training size changes. It's like your world size changes. So now you can either give less data to every node, right? And they train faster, but that's not the same, because usually when you do centralized training, like everything stays the same, constant, right? You have a learning rate decay, and every batch size stays constant. Some do a learning batch also like decay, but it's like it's controlled. But in this case, it's not controlled, where some nodes just drop out, and now you have to deal with it. And how do you keep the optimization stable? And that is kind of coupled with the optimization process itself. If you only solve kind of how to balance the nodes and how to ensure that people don't drop, the optimization, like the model itself at the end, might not be good still. So you want those two are kind of joint together.
Thank you for the great talk. I have a question in regard to RL in pre-training. We know that RL is a great technique for post-training, but have you explored its efficacy in pre-training stage? Thank you.
Yeah, so there's I think a few papers that just came out talking about like reinforcement learning during pre-training, right? So we didn't do anything yet for that, but we're planning to try like some things as we successfully pre-train some models. So the first really important part is to replicate those centralized runs, and those are very difficult to replicate because we don't have access to that many compute. So they can do ablations on very large models, 70B, right? Like they can do 5 models in one day, but we can't. The 70B is our last run. So we do ablations on very small models, and we hopefully can replicate like the training for centralized baselines. But until then, we won't really explore like two like novel architectures. But the most important part is really to make the training process work.
Sorry, here. Thanks for the talk. You mentioned like asynchronous updates,
yes,
like, as one of the optimizations needed. Like, Do you know if this is something that's in the works? Are there people already doing this? You know how mature this is?
So right now, the two kind of schools of decentralized training are either using gradient compression or asynchronous training. So there's some people using, for example, DLoco, which is a asynchronous training method, and that works. But when you try to scale that up, it's very difficult. When you have more and more islands, it's very difficult. Same thing with gradient compression. So right now, it's really an open question. These papers are fairly new. So they're all like from 2023 and onward. So it's still ongoing research, and no like big labs are using these kind of algorithms yet.
Hi, yeah. I'm curious as to what you think some of these strategies for decentralized training can reveal about pre-training dynamics. Because from my understanding, as much as we do know about pre-training and how it works and why it works, there's still a lot fundamentally that we don't know, which is why we have so much innovation in the field of optimizers, where people are, mathematically proving, but first creating new optimizers without proofs behind them that seem to optimize better. So do you think with some of the strategies being worked on for this kind of decentralized pre-training, both synchronous and asynchronous, both in optimizer categories like Demo, your paper, as well as things like DLoco, do you think we are coming closer to an understanding of what exactly is happening during pre-training and why some of these strategies work and some don't?
Yeah, I think that's an ongoing process, because if some of the processes work, for example, gradient compression, we know that the training process is sparser than we thought, right? And if the asynchronous training also works, that means that the data is much more like IID than we thought also. So these are very like ongoing processes. I can't really tell you like directly if we've learned exactly like we've learned something from this, but I do know that from this research and doing decentralized training can allow more people to do this kind of research. So when decentralized training becomes mainstream, people can just pay a little bit to do pre-training research instead of like kind of like paying a lot for the big runs, right?